Okay, the second lab of the refrigeration cycle we will focus on the condenser. Okay, we will look at the detail in the condenser, the heat transfer in the condenser. Okay, as you know, a condenser is a heat exchanger, right? In this lab, it's a water-cooled condenser. Okay, water as a heat exchanger fluid. Okay, so the water goes through the heat exchanger, goes through the condenser, removes the heat from the refrigerant. Okay. So the energy has to be balanced in the condenser. So the loss of energy, the loss of heat in the refrigerant side will be equal to the heat gain in the water side. Okay, that's the energy balance. You will need to use this energy balance to calculate the mass flow rate of the refrigerant. Okay, so that's the first goal in the second lab, is to find the mass flow rate of the refrigerant. Okay, so remember the heat gain and heat loss calculation. Okay, the heat lost in the refrigerant side is a mass flow rate times delta H, right? If you measure the enthalpy of 1 and 4, so you will have a delta H. So delta H times the mass flow rate will be equals to the heat gain in the water side. What is the equation for heat gain in the water side? M dot C delta T, right? M dot is the mass flow rate of the water. Okay, so mass flow rate of the water is displayed on the unit, so you will see that unit. You will see that value. Okay, delta T is what you need to measure. Okay, the water is just room temperature water entering the condenser, so it's room temperature about 75 degree. Okay, then the water leaves the condenser will be hotter, right? So you will need to measure that water temperature. So you have the delta Tc, you can find it. And the mass flow rate of water is shown, okay? So the total heat gain in the water side can be calculated. Okay, that will be equal to the heat loss in the refrigerant side. In the refrigerant side, m dot delta H. Delta H, you can measure it. Okay, so in that sense, you can calculate the mass flow rate of the refrigerant. Okay, so for the measurement, you need to measure at the same time because you are looking at equilibrium. So in reality, one student maybe measures the refrigerant side, one student measures the water side temperatures at the same times. Okay, so you can reach a better measurement because it's an equilibrium. So you better measure at the same time. In this lab, you're also required to calculate some other performance characteristics of the refrigeration cycle. Two of them, compressor efficiency as well as the coefficient of performance. Okay, compressor efficiency is defined as W, the work of the compressor, ideal divided by the actually work of the compressor. And it's equal to, look at the diagram, H2S minus H1 divided by H2 minus H1. 1 and 2 are the 2 points before and after the compressor. So H2 minus H1 is the actually delta H, right? You measured. H2S is the isentropic line based on 1. Okay, so after you measure the H1, look at this diagram. It's located inside the dome, located in the vapor region, right? If you draw a isentropic line from 1, you will get a ideal 2S. Okay, so use the H2S minus H1 as the ideal isentropic work of the compressor divided by the actual work of the compressor, which is H2 minus H1. Then this is the compressor efficiency. Okay, so this is the compressor efficiency. The next one will be the coefficient of performance, beta, which is the heat transfer rate divided by the compressor heat transfer in. So remember which part is heat transfer in? That's evaporator, right? You receive heat from environment. So it will be H1 minus H4, delta H before and after the evaporator, divided by H2 minus H1, which is the compressor. Okay, so this ratio is the coefficient of performance of the refrigeration cycle. Okay, so three things you need to calculate, find from this lab is first one is the mass flow rate of the refrigerant. The second is the compressor efficiency. The third is the coefficient of performance. Okay, so after this measurement, after this lab, you will have a understanding of the refrigeration system.